What gives people feelings of power? Is it money? Status? What if I told you that there was something that could make billionaires and monarchs drop everything and run? But to some, this is something that can hold utmost beauty and joy. This thing that some fear and others revere is math. And today, I want to give you a glimpse into the elegant patterns and euphoria of discovery math can hold. I want to take something that at first just looks like fear-inducing mathematical symbol soup and show you that buried deep at its heart are hidden connections, seemingly unrelated patterns that all come together and make sense at the end. And trust me, the feeling of joy you experience when you finally understand where this formula comes from, there's almost nothing that can rival that. Let's embark on a journey where we derive the binomial theorem from scratch. But first, what is the binomial theorem and what does it mean? This looks really complicated, but all this formula is telling us is how to expand a plus b raised to some power. Now what do I mean by that? Let's say you have a binomial and you want to cube it. That just means multiplying a plus b by itself 3 times. To simplify this, we need to use the distributive property of multiplication. The distributive property of multiplication basically tells you how you can multiply a number, say 5, by the sum of two other numbers, say 3 plus 4. 3 plus 4 is 7, so this is 5 times 7, which is 35. But another way you can do this is multiply 5 by 3, then multiply 5 by 4, and add both of them together. So generally, we can write that a number x times the sum of two other numbers a plus b is equal to x times a plus x times b. Now returning to our initial expression, we use the distributive property to expand this out. And now we do this again, and we get this mess at the end. But fear not, because this can be simplified. We just add like terms, and what we're left with is a plus b whole cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b squared. Now this was fairly easy and straightforward, but imagine doing all this work to expand this monstrosity. We need to find a quicker way, perhaps a pattern in the terms of the expanded expression, a way to jump directly to the expanded form, skipping all the steps in between. And to do that, we need to examine the very nature of multiplication itself. Let's try expanding a plus b whole cubed once again, but this time I'm going to color code the variables depending on which binomial they come from, so we can keep track of what happens when we expand this expression out. So let's use the distributive property once, and now there are a total of 2 terms, one that has a factor of the blue a and one that has a factor of the blue b. Let's do this again. The number of terms doubles again, each term splitting into a version of that term with a factor of the green a and a version of that term with a factor of the green b. And we repeat this process one final time, each term splitting into 2, a version that has a factor of the red a and a version that has a factor of the red b. Perhaps you've gotten a vague sense of the nature of binomial multiplication. Each term in the final answer is just the product of 3 numbers, one taken from each binomial. This is because of the very nature of the distributive property. So now we have a new way to expand a plus b to the power of n. You first write it out as a plus b multiplied by itself n times. Now from each binomial you choose either an a or a b, and you multiply all your a's and b's together. This is one term of the expansion. To find the rest of the terms, you need to do every other possible way of choosing a's and b's from each binomial. You add all the terms of the expansion together and voila, that's your answer. But we still have a long way to go. The first obvious thing to do is to write each term using exponential notation. Let's call the number of a's in a term k and the number of b's in a term l. Each term is of the form a to the power of k times b to the power of l. But notice something interesting. We multiplied n binomials together, and for each term we chose either an a or a b from each binomial. Therefore, we made n choices, and the total number of a's and b's in each term is equal to n. This means that the power of b in each term completely depends on the power of a in that term. Both the powers add up to n. K plus L is equal to n, so we can represent each term in the expansion as a to the power of k times b to the power of n minus k, where k is the number of a's we choose. K must be in between 0 and n, inclusive, since we can't choose less than 0 a's or more than n a's, since there are only n binomials to choose from. Now, there's one final step of simplification. In our expansion, we have a lot of terms that are equal to each other. We can add all these duplicate terms together. To do this, we need to know how many of each duplicate term are there. So let's ask ourselves this question. When do we get 2 or more terms that are equal to each other? Well, the value of each term only depends on the number of a's that were chosen. So if we choose the same number of a's in different ways, we'll get multiple terms that are equal to each other. Here, let me explain. Let's say I'm choosing a's and b's for one term of the expansion. Perhaps I choose these 2 a's and a b from the remaining binomial. Here I've chosen 2 a's. The value of k for this term is 2. Now, for a different term, I could choose these a's here. This is a different possible way of making a term, but the value of both these terms are equal. So now we can see that the number of times the term a to the k times b to the n minus k is repeated in an expansion is the number of ways you can choose k items from n items where order doesn't matter. And we know that the number of different ways you can make a group of k items from a total of n items is given by this combinatorial formula here, or simply represented by the symbol n choose k. And now we have everything we need to expand binomials raised to a certain power. So let's put it to the test and try to expand a plus b raised to the power of 10. We know that each term in the expansion will be of the form a to the k times b to the 10 minus k, where k is an integer ranging from 0 to 10. However, some terms might be repeated in the expansion more than once, so we can add a coefficient to each term, which represents the number of times that that term is repeated. Now, if the power of a in a term is k, the number of times the specific term is repeated is the number of ways you can make a group of k objects from a total of n objects. We can evaluate that at each coefficient, and that's it, we're done. All that's left to do is give this method a fancy name. How does the binomial theorem sound? Write it using fancy math notation, and now you're ready to teach it to students around the globe. But it doesn't have to be this way. It shouldn't be this way. Math is about understanding why stuff works, not about memorizing complex formulas. It's about finding connections between things and discovering the mysterious and elegant patterns that arise. Thanks for watching.